Good afternoon, everyone. Thank you for coming. It is my pleasure to give a talk of my research today. This is not only a talk, but it's also my oral defense, dissertation oral defense. So your attendance and your encouragement will make my day. And first of all, my name is Su Yifan, and my advisor is Dr. Huang Zaoli老师. And the issue I'm going to talk today is the interplay between simulation and phosphorylation. This is a relatively big issue, and I have two topics that covers this. Before I start these two topics, let me first brief you through the backgrounds of simulation. Sumo pathway is a series of transporting process of the sumo protein from several sumo mechanism components to its target protein. And when a newly translated sumo protein, it is in an immature form. And this immature sumo is first converted from immature form converted to a mature form of sumo by the isopeptidase. And later on, this mature form sumo will be activated by the E1 activating enzyme through the conjugation of the thioester bond. And later, the sumo will pass over from the E1 enzyme to the UBC9 conjugation, which is conjugated with the thioester bond. And afterwards, with the help of the E3 ligase, UBC9 will transfer the sumo to the target protein through the isopeptide conjugation. In the end, sumo will be removed from its target by the isopeptidase. Now, like other post-translation modification, simulation also play many roles in biological functions. For instance, bioreplication, carcinogenesis, cell signaling, cell cycle, and transcription. And the two topics of my talk today covers we have relationship with transcription and cell cycle. Now, many reports also found that sumo modification cross-talks with other types of protein modification. For instance, acetylation, ubiquitination, and also sumo-lase itself, and also phosphorylation. Like there are some examples shows that kinases and phosphatidyls can be sumo-related, and also sumo machinery components can be phosphoregulated, and also at the substrate level, its phosphorylation, its simulation can be enhanced or inhibited by phosphorylation. So, why do we study phosphorylation and simulation? First of all, this last study, and it's relatively new, and especially the crosstalk between the sumo components and the phosphorylation. Now, for just take UBC9 or E1 enzyme for example. In simulation, there's only one E1 and one UBC9, and don't you think that it is incredible for just one E1 or one UBC9 to regulate the whole global simulation? So I assume there must be some kind of extra energy which helps or pushes the regulation, their function. So therefore, we are interested to having better insight to see the linkage between the phosphorylation and simulation machinery. So this will lead you all to my first topic. My first topic is phosphorylation of UEC9 by CDK1-cyclin-B enhances the simulation activity, and it is just recently published. And first of all, what we did was we used several different kinases and tested if these kinases will have an effect on the simulation activity. Okay, we used these kinases, the CDK1-cyclin-B, CDK2-cyclin-E, ERK1 and 2, PKA, and JAK kinase. Okay. If you look at the top panel, in the increasing concentration of the CDK1-cyclin-B, you will see there's the increased simulation activity in the concentration-dependent manner. It stands out from other kinases because if you look at the simulation activity by other kinases, it seems that the simulation activity is not affected by the rest of the kinase.
But I don't quite agree. If you look at ERK1 or ERK2, I thought they are also increasing. Or even PKA.
But if you compare the intensity, compare these few kinases, my personal feelings is that CDK1-cyclin-B stimulates greater than, has a greater stimulatory effect greater than other kinases. That's my personal feeling. So that's why we think that CDK1-cyclin-B is one candidate that we can further our studies. Yeah. So the substrate material that we use is a short peptide of the human topoisomerase 1. And because we want to see if the crosstalk, whether the crosstalk between phosphorylation and simulation machineries, so we first just mutated the serines in a terminal part to the alanine, just to make sure that the kinase may not target to the substrate. And the advantage of using this substrate is that it contains a known sumo recognition motif, this part, and it is easy to prepare, like it's easy to express and easy to purify, and also it's relatively stable. And just to for knowledge, sumo recognition motif consists of these 4 amino acids. The 5 stands for the hydrophobic residue, K is for lysine, X for any residues, and E is for glutamic acid. Now, the previous result indicates that CDK1-cyclin-B stimulates the simulation activity. So let's briefly talk about the background of the CDK. Now, CDK plays an important role in ensuring the proper cell cycle regulation when it associates with specific cyclins in a specific phase and for specific functions. Now, a brief introduction of this kinase. Before the cyclin B, before cell cycle goes into the mitosis, cyclin B is synthesized in G2 phase. And then cyclin B will associate with CDK1 before and triggers the mitosis. And this kinase complex phosphorylates more than 70 proteins and it regulates the chromosome condensation with Golgi network fermentation as well as nuclear envelope breakdown. Lastly, CDK1 will, this kinase is inactivated to exit mitosis through the degradation of cyclin B. Now, the indispensable role of simulation in the cell cycle, particularly mitosis, can be seen throughout different species. Like for instance, I show here in the lower eukaryotic fission yeast, it has the sumo homolog called PMT3. The disruption of this PMT3 will show a defect in mitotic structure and segregation error. Now for its sumo protease in the body is called ULP1, its mutant will cause a cell cycle delay as well as the chromosome misactivation. If you look into the higher eukaryotes like mammalian, rank F1 requires sumo 1 conjugation for its targeting to the kinetochore and mitotic spindle. Okay, simulation is not just about clicking mitosis. Simulation dynamically and timely regulates to ensure proper cell cycle progression. I give you a few examples, like the PML and S300 nuclear bodies, part of the nuclear body components. They are simulated during the interphase, but they will be destimulated before they enter mitosis. Just for your information, interphase it covers the G1S and G2 phase, and M phase. Okay. And then topoisomerase 2 is sumo 2/3 modified during the metaphase, and it's rapidly destimulated once it wants to get to the anaphase. So it's pretty short time. So, okay. After you see this result, it gives us a hint that simulation and CDK1 phosphorylation may have some kind of cross-talk to ensure a proper cell cycle progression. So we first would like to analyze which of the components of this is the target of CDK1 cyclin B. Could it be substrate? Could it be sumo or UBC9? We don't know yet. So we first tested CDK1 and substrate. We conducted an in vitro kinase assay using the P32 radio labeling. And in the increased concentration of the CDK1 cyclin B, for information, the left part is the ultraradiography, and the right is the Kamasi blue staining, which you can see the protein sites. So in this Western, that's not Western. In this result, it is obvious that substrate, there's no phosphorylated phosphorylate signal that is occurred by the CDK1 cyclin B. If you compare this to the protein size in the Kamasi blue staining. Next, we also see whether the kinase will phosphorylate the E1 enzyme or the sumo1. In the upper level, we tested the E1 activating enzyme, and it's obvious that we don't see any phosphorylation signal in two of the components. Okay, and we also tested sumo1, and also the same, sumo1, we don't see any phosphorylated signal in the ultraradiography. We compare both of them to the Kamasi blue staining on the right. So, if I don't see these components to be phosphorylated, could it be UBC9? So the answer is affirmative. Okay. In the presence of CDK1 cyclin B, we see there's an increased phosphorylated signal in this ultraradiography compares to corresponding to the protein size on the right. So, a short summary: CDK1 cyclin B stimulated simulation is independent of substrate phosphorylation, and this kind specifically phosphorylates the simulation machining component, the UBC9. As a result, it increases the simulation activity. Now, in fact, UBC9 also plays a role in cell cycle, and it's across different species. Like for budding yeast, the UBC9 deficiency causes inviability, whereas in the fission yeast, the UBC9 mutant, the mutant is called Hus5. The mutant of this protein displays defects in chromosome segregation and reduced cellular growth. Well, if you look at the higher eukaryotes like mouse, the loss of UBC9 in the mouse embryo results in chromosome misactivation and loss of the nuclear integrity. And zebrafish UBC9 requires UBC9. Zebra Phillips requires UBC9 for the G to M transition during the organogenesis. So, since we know that CDK1 only mediates phosphorylation of UBC9, and this phosphorylation will stimulate the smolation activity. So, in order to prove this case, we generated phosphorylated UBC9. So we see if this phosphorylated UBC9 without the kinase can enhance the smolation activity. So this is how it's done. First, we pre-treated the UBC9 with the GST text CDK1 second B in two sets. One is with AT, the other is without ATP. And then the reaction mixtures were passed through the glutathione resin, and this is to remove GST text CDK1 second B. And later on, we collect the flow-through, which contains the phosphorylated and non-phosphorylated UBC9 for our in vitro assay. And this is the result just to show you that the GST tag CDK1 cyclin B is removed and retains on the glutathione resin. And you can see that the flow-throughs that contains the non-phosphorylated and phosphorylated UBC9 are kinase-free. So we use the flow-throughs and use them for our following simulation assay. Okay, in this result, the non-phosphorylated UBC9 is used on the left and phosphorylated is on the right. So it is obvious here that it's clear that the phosphorylated UBC9 enhance the simulation activity in about twofold greater than the non-phosphorylated, the simulation affected by the non-phosphorylated UBC9. So, in summary, CDK1 cyclin B phosphorylated UBC9 increases simulation activity. And next, we'd like to test if this kinase will affect the conjugation activity of SUMO1 with the E1 enzyme, as well as the SUMO1 with the UBC9. First of all, if you still remember the slide that I showed you earlier, SUMO1 is activated by the E1 enzyme through the binding of thionyl acid bond. So we want to see if the CDK1 would affect the intensity of the thionyl acid bond between these two. So we first treated the CDK1, the SUMO1, E1 with ATP in a non-reduced condition. So here, the Western, we probe this with the E1 antibody, and it shows that with the increasing concentration of CDK1, the thionyl acid linkage between SUMO1 and the E1 enzyme is not affected at all. So suggesting that thionyl acid bond formation of E1 enzyme and SUMO1 is irrelevant to the CDK1 treatment. Then we next test that is there any difference between the SUMO1 and UBC9. For information, the conjugation between UBC9 and SUMO1, there's two binding. One is thionyl acid bond, the other is isopeptide bond. To see if the bonding is affected by the CDK1, we treated the kinase SUMO1, E1, UBC9, all these components together with ATP in two sets, one in the reducing condition, the other is non-reducing condition. So if you look at the bottom panel, this is the reduced condition assay, and you will find that because reduced condition, the thionyl acid completely wiped out. Now there's only isopeptide bond linkage in this conjugation, and you see the conjugation, the isopeptide conjugation is not affected in the increasing concentration of the CDK1/2B. Now, if you look at the upper panel, which is in a non-reducing condition, there are two types of binding. So you can see that the summation of the isopeptide and the thiol acid conjugation molecular species is increased in concentration-dependent manner. So if you subtract the upper panel with the bottom panel, which isopeptide bond is not affected at all, you will get increasing concentration dependent manner of the thiol acid linkage. Okay. So we conclude that the thiol acid bond conjugates between UBC9 and SUMO1 was enhanced by the kinase. Just a small summary that CDK1/2B enhances the thiol acid conjugation capacity, but not the isopeptide conjugation of the UBC9 with SUMO.
So I'm not clear about the details of this reaction. So
okay.
What's the relation? The SUMO1 linkage with UBC9. Is that UBC9 gets SUMO-related, or is totally different from the SUMO-related?
Because they will bind together with two types of bonding. One
of them is similar to the SUMO-related substrates?
Yeah.
So is there a CDK phosphorylation site? Where is the phosphorylation site?
You mean on UBC9?
Or it's not affected at all?
Oh,
right?
Actually, I will tell you that in the later slide. Yeah.
So have you done, for example, you remove lysine, there's can link this isopeptide bond linkage with the SUMO?
We haven't done that, but I know that there is a few simulated lysines which can be simulated in the UBC9. We haven't tried that yet. Yeah.
Multiple lysines.
Sorry?
Yeah, multiple lysines in UBC9, they can be.
So there's like the 153, 157. Yeah.
That's Easter.
That's
Mammalian. So mammalian, you should know at least we identify 3 SUMO-relation sites.
Yeah.
One is at 13, one is at 55, and I think one is at 70 somewhere.
This is made it.
Yeah.
Yeah.
Okay. But you said that you're going. My question is, are you going to show the relationship between the phosphorylation and SUMO-relation site?
Yes.
So you will show those sequences, right? The relative positions of the phosphorylation and the SUMO-relation site on UBC9.
Yeah, actually I did some experiments to show that where's the simulation.
Yeah.
Yeah. We can discuss it later. Okay, we next test if CDK1/2B stimulates the simulation of a more physiological significant substrate, the human, the full length of human topoisomerase 1. Okay. It is obvious here that in the increasing concentration of the CDK1/2B, right, it enhances the multi-simulation of the human topoisomerase 1. I have mentioned to you that the human topoisomerase 1 contains multi-simulation site, non-simulation site, and most of them are located in the N-terminal of this protein. So it's obvious that CDK1 enhances the multi-simulation of this protein. And we also tested the simulation level of the human topoisomerase.
What's the E3 in that reaction?
Sorry?
What's the E3 in that reaction?
We did not include E3 in the in vitro assay.
So UBC9 E2 can directly transfer to the substrate.
Yes.
In vitro.
Yes, that's the only in vitro. Yeah. So we also examine if the simulation of the topoisomerase 1 that contains only the N-terminal part, 1 to the 200 amino acid by the phosphorylated UBC9 and non-phosphorylated UBC9. So this time we don't include the kinase, we only use the phosphorylated and non-phosphorylated UBC9. So in this result, it is very clear that, just to mention that E2 stands for the non-phosphorylated and PE2 is phosphorylated UBC9. So it is clear that the phosphorylated UBC9 is able to enhance the multi-simulation of the human topo 1 greater than the simulation from the non-phosphorylated E2. And the phosphorylation is enhanced in a time-dependent manner. And the right panel is just to show how much amount of UBC9 used for the assay. So CDK1 cyclin B phosphorylated UBC9 stimulates multi-simulation of the full-leg human topoisomerase 1. Since we already know UBC9 can be phosphorylated by this kinase, it would be fantastic if we to find out the phosphorylation site of this UBC9. So to do this, we thought of using the mass spec approach. Okay, and this is how it's done. First, we treated the UBC9 with CDK1 cyclin B with and without the ATP. And later on, the reaction mixture passed through and is subjected to an in-solution digestion. And the digested phosphopeptides were enriched with the immobilized metal affinity chromatograph. And later on, the elutions were forwarded for the LC mass analysis. Okay, the LC mass analysis shows that there is a phosphorylated serine at the serine 71 on the UBC9 peptide, and whereas there is no phosphorylation is detected on the other serine. We also tested whether I should say that we actually also mutated the series of this peptide, okay, the 70 and 71, and use this mutant to do a simulation assay to compare with the wild type. And we found that the UBC9 mutant losses enhanced simulation activity compared to the UBC9 wild type in the concentration dependent manner. So, summary is CDK1 cyclin B enhances the simulation activity through the phosphorylation of UBC9 at the serine 71.
So why didn't you do just 71 mutation?
Actually, we did this at the same time, and I predicted myself. So I thought that this series might be potential. It has a potential. Yeah, and luckily I got them both correct. Yes.
And what about S71D?
Oh, I haven't tried that yet because I was really that's a good approach also. I actually need to try that. Yeah. So the conclusion of the whole study, CDK1 cyclin B stimulates simulation activity compared to other cell cycle related kinases, and this kinase specifically phosphorylates the simulation machinery of UBC9, but not the substrate, and it phosphorylates particularly on serine 71. This kind CDK1 cyclin B phosphorylated UBC9 exhibits the elevation of simulation activity and it also stimulates this, multi-simulation of the full-length human topo isomers 1. And this kind of enhances the thionyl acid conjugation between UBC and SUMO1. Okay. The significance of this study, well, two significance of it. One is it provides new, as well as the first evidence, which the UBC9, part of the SUMO machinery component, can be regulated by phosphorylation. And another thing is it provides a broad implication in cell cycle regulation, which phosphorylation of UBC9 may play a role in mitosis. So hopefully you're still awake. And I have just a second topic to
I
go.
thought you were going to show the phosphorylation side and SUMO side of UBC9. Relatively possible.
So we tested whether there's any phosphorylation site on the UBC9. So we want to test it, so we can only try the mass spec to see if we can get any peptides that is phosphorylated by CDK1. So I think this is one of.
Because you introduced the relationship between phosphorylation and SUMO site, are you sure that SUMO consensus? I'm just curious. On UBC9, what's the relative position of this?
With the lysine, you mean?
With the lysine.
With the lysine, but the study that we focus on is the substrate away from the simulation, which is we first don't consider UBC9 as a substrate. We consider other substrate proteins as target. So
your argument is trying to say, I thought you were trying to argue phosphorylation on UBC9 enhances home simulation also, or no?
No, I misunderstood your question. So the purpose of this study is to see whether a phosphorylated UBC9 can, or I should say that CDK1 mediated phosphorylation of this UBC9 will affect its downstream simulation target. That's our focus on this study. Yeah.
So it's a series 71 conserved recipe.
Series 71.
This is the mammalian one. How about yeast?
We did not look into yeast.
Oh, you don't have to look at it. I'm simply asking you. That has to be conserved.
I think it should be conserved.
I think what's happening here is that this experiment is always very nicely done. You have the beautiful in vitro system. But it'd be nice to have some in vivo significance attached to it. So the easier one is simply to have a evolutionary sort of conservation. At least you show that 71 series is a conserved recipe. Then you can argue the phosphorylation might be significant in the intracellular regulation. So that might be a good way to include that in your thesis.
I appreciate very much for this suggestion. I'll try to do this.
Of course, in the future, if someone else is going to do it, if the yeast has it, then you can do the mutation. Then it'd be nicely done. Otherwise, in the mammalian cell, you have to knock down the original one, replace with a mutant one. It's a little bit more complicated.
Right. Okay.
Because it really needs in vivo.
Right.
Yes. Kind of data to support.
So let me just bring you to the other topic of my talk. Okay. The second topic of the talk is the phosphorylation-dependent simulation of transcription factor NFE2. Okay, NFE2 is basically using zipper heterodimeric transcript factor. So it consists of a P45 and P18 subunit. P45 is a large subunit that contains the transactivation domain and the DNA binding domain. Whereas the P18 is a smaller ubiquitous subunit, and it is an obligatory binding partner of the P45. And this transcription factor plays an essential role in regulating erythroid and megakaryocytic genes like alpha, beta genes, thrombosis synthase genes.
So what is phosphobilinogen gene?
It's a gene that
It's a protein. And what does it do?
it functions for the red blood cell production. So because NFE2 plays a role in regulating erythroid and megakaryocytic cells, the protein that is that functions in this kind of cells. Several importance of NFE2 development is shown in this slide, like the murine erythroid leukemia cells. When it's lack of P45, it shows a reduction in the globin gene expression, whereas the mouse, which lacks of the NFE2 transcription factor, will cause a thrombocytopenia accompanied by defects in platelet production, which means the platelet production has failure. And when in human, who develops the polycythemia vera disease, presents abnormal expression of the P45 NFE2, lower levels of the red cell production, and as well as thrombocytopenia. Now, earlier findings have shown that the transcription activity of the P45 NFE2 can be regulated by the simulation of P45, cyclic AMP-dependent protein kinase, and RAS signaling cascades. And as a matter of fact, the study shown above I say that there are several studies that show that some of the transcription factors, the simulation of this transcription factor can be positively regulated or negatively regulated by phosphorylation. So by comparing these few examples, these studies, it gives us a question: are there any interplay connections between phosphorylation and simulation of P45 and NFE2? So in order to address this question, we thought of using in vitro system, but we have to obtain a purified heterodimer to do the study. Now, we first expressed this protein, this heterodimer P45 P18, using the baculovirus expression system. Okay, and then the cell lysates of this heterodimer were purified using the specifically designed purification method. We first purified the lysates with ion exchange chromatograph, and then the fractions were further purified with a nickel affinity purification. And the reason of using this sort of strategy is because P45 and P18, both of them carries two different extreme isoelectric point value. P45 carries 4.8 and P18 carries 10. Now, and we suppose that the heterodimer P45 P18 complex will have different PI values comparing to 4.8 and 10. We assume there's difference, so it can be isolated using the ion exchange chromatograph. So we use the molecule and ion exchange resin to do this purification, and the fraction that we collected, we individually purified with the nickel affinity column. So as expected, we are able to isolate the P45 P18 complex in the point. This is very small. 0.3 to 0.6 molar of the NaCl in fraction 11 and to 14. You can see this in the Western blot. By probing with the anti-P45 P18 antibody, you see fraction 11 to 14 with the P45 and P18 are co-eluted in the fraction. And you see only P45 alone eluted in other fractions. And we pull them together and further purify with the nickel-filling column. And here, just to show you that P45 P18 complex purified here, and this is P45 alone. Now, as I mentioned in the earlier slides, that P45 and Fe2 is regulated by simulation, as well as cyclic AMP dependent pKa. So we want to test if pKa will affect the simulation of P45 and Fe2. So we first did an in vitro simulation assay with the sumo machinery complex components. We added pKa and we added the complex of P45 P18. We see that the simulation of P45 is increased in a concentration dependent manner. But if you look at the bottom panel, which P45 alone is used, even though pK is enhanced in a concentration dependent manner, increasing, the simulation of P45 is barely detectable. Okay, it suggests that pKa may enhance the simulation of P45 complex. Now, we also look into P18, whether the simulation of P18 can be enhanced by pKa. If you look at this part, the P18 simulation is increased. Okay, but we also tested if P18 alone, whether it can be enhanced by the PK kinase. Here, without a pKa, P18 alone is simulated. But if you add a pKa inside, the simulation intensity of P18 is increased. So this suggests that P18, the simulation of P18 can be enhanced by pKa, but the simulation of P18 is irrelevant, is regardless to its formation with the P45. So which means it itself can be simulated and enhanced by
Can you
pKa.
go back to the previous one?
Right.
So the left two lanes on the top panel.
Okay.
Oh. But here, did you see any increase of the P18 simulation?
Well, if I judge it from the basal non-simulated P18. So because the non-simulated P18, there's an increasing tendency, decreasing tendency of the non-simulated P18. So we judge that there's probably enhanced simulation of the P18 and it's by pKa.
So why do you see the sumo P18 at all without ATP?
Could you
Look at the first name on
yeah.
the top panel.
Right.
Why did you see sumo like the P18 at all?
Right. For this one, this is I've tested this. I didn't show this slide. I tested this. It's probably it's caused by the non-specific background by antibody. By the antibody I used, P45 P18. Yeah.
You're sure of this?
I'm sure I can show you.
Because there shouldn't be any simulation
No.
without ATP, right?
So, sorry again?
There should not be any.
Yeah, there should not be any simulation.
So actually, I want to see a control of the pKa minus ATP. But unfortunately, ATP is used both in pKa and in SAY1 and SAY2. So So we can't really do that experiment. Is there any way we can do it?
So you were saying that if we can.
So in other words, what if I say that it has nothing to do with phosphorylation? It's just the additional pKa did that.
Oh, you mean pKa?
So we can't really do the minus ATP control because of your individual system.
Minus ATP, which means that if I just do the phosphorylation P18, you mean?
No.
Actually, we should have an increased pKa and without adding ATP.
Oh, you mean the ATP? You were saying that ATP might cause the background.
No, I'm asking, what if I argue all this effect is due to the addition of pKa?
No,
And
due
you
to
want to argue it's
phosphorylation.
due to the phosphorylation. Anyway, we can discuss it.
I need to.
Yeah, you can do you can do an experiment by stepwise, but anyway.
Okay.
So the next problem I still also have some question. What's the difference between right part panel and left panel?
Oh yeah, this is a mistake I didn't show. I forgot to show this. The right panel is actually the mutant form of the P18 because P18 is known to be stimulated and it's stimulated at lysine 14.
Mutant
So
PAT.
yeah, so this is supposed to be the mutant P18. So without the stimulation site, you will never see for stimulated P18.
Okay, so and then there, the second one is the gel may not be that clear. The second and third lane, you don't think that the P18 amount in the third lane is more than the second lane?
Okay, so I guess it's probably the loading mistakes. You mean that there's probably an how do you say loading error?
No, I'm just questioning whether that increases, how much of that increase is real?
Oh, okay. I think probably you can't see it this way because the non-stimulated P18 is too thick. So, and this is my explanation. Probably because it's too thick, you can't see too much different. Whether it's there's some part of the P18 has elevated. Do you understand?
I'm just saying the both bands in the third lane are, let me see, 2, 3, 4, higher than the second lane. So how do you know it's not a loading?
2, 3, 4.
The lower band looks to me is twofold at least, but maybe it's because of overexposure.
So
I don't know
it's
whether
the
they have other type of gels.
Is the increase real or not? Because you can see the third lane, the PAT is the level on the third lane, the PAT is always higher than the second lane. So
I think I could only say this is probably overexpressed, and if you're not overexposed, if I don't overexpose, it probably the intensity is much lower.
Then in the season, you probably should substitute a better gel. You should show people that it's really have an increased stimulation in the presence of the. You must have multiple gels like that.
Yeah, I feel. And
The other gel, it doesn't show this, it's clear that you have.
the difficulty is this experiment is very difficult to do because the PAT is very unstable. You cannot express only PAT. The PAT must form complex with P14, and you can form, then the PAT becomes stable. Otherwise, your PAT cannot very unstable.
I know, but you must have done twice or 3 times.
Yeah,
All the
yeah.
gel must have equal loading.
yeah, right. But I didn't show it. I've done several of those, and probably this is the best result again, but I didn't. I mean, I didn't notice the loading of this result, so therefore I put this one in.
I think if we want to resubmit this paper, we should repeat this experiment and also previous experiment.
This one.
Yeah, because in the absence of ATP, you also see phosphorylation of PAT.
Yeah.
I know the PAT, that band is the background.
Yeah.
So, anyway, that people may not accept it.
I understand your argument. I think later on I will try to probably to repeat these experiments and try to make sure that the loadings are okay. So people won't argue this point whether it's simulated or not, or whether its simulation can be affected by pKa.
So how pure is this PAT or P45 PAT prep? Can you do a Kumasi stain to visualize?
I did not put the Kumasi stain on this.
You can do the Kumasi stain, then you can address, Professor
Right, yes,
Shi's
yes,
question,
yeah,
right?
yes.
That's what usually people do, just do a Kumasi stain, then do all the rest.
Okay, I understand. Okay.
Or show previous slide. Or you can have the substrate unknown without adding sumo 1, UBC9, and the E1.
Just to see if there's
The
background.
substrate unknown.
Yeah,
You also see that thing.
right.
It's a
Then you
sandwich.
can judge whether that's background.
Background could be coming from.
Yeah, right.
Protein
Unfortunately, we had the same position at the phosphorylation side.
Because your baculovirus prep is only 2 columns.
No.
Background.
Only 2 chromatographies.
One is molecule, one is.
Yeah.
So my suspicion, unless you have much better luck, my suspicion is probably not.
Okay.
So it could be coming from that.
Okay. Actually, purification is quite tough.
I understand that.
Okay. Right. Let's move on. We also examine whether earth-1 phosphorylation may also affect the simulation at P45 and P2. And so here we did the same in vitro simulation assay in the presence of earth-1. So the upper panel is the complex that are used, and the lower is P45 alone. So if you look at the upper panel, when there's no earth-1 added, the simulation activity is pretty low, and once earth-1 is increased in the concentration increased, the simulation of P45 and P2 is increased as well. If you look at the bottom panel, where P45 alone is used, the simulation of P45 is not enhanced at all. It's undetectable. So it suggests that earth-1 may also enhance the simulation of P45. And so the conclusion is we have successfully co-expressed P45 P18 complex through the baculovirus protein expression system. And P45 P18 complex can be purified through the ion exchange and the nickel affinity method. Because PI value of P45 and P18 are extremely different from the NFE2 heterodimer. Also, simulation of P45 and NFE2 is enhanced by phosphorylation mediated by PK and F1. And simulation of P45 requires its formation with P18 as a heterodimer. And P18 can be simulated both with or without forming heterodimer with the P45. So the significance of this study, I have to, and transcription quality of NFB2 may rely on the co-regulation of simulation and phosphorylation by PK and kinase. And second one, the proper physical configuration of NFB2 is required for effective simulation of P45. And that's the end of my second topic.
But in this part, that you have enough protein, right, of the NFB2 purified. I'm just curious why you didn't map phosphorylated sites as you did in the first part.
Oh, actually, I'm thinking of to continue the study. I haven't done it yet. I'm thinking of whether I could find the phosphorylation site on P45, where the ERK1 recognition site, PK recognition site has been found already, but ERK1 hasn't. They haven't mapped the ERK1 recognition site yet. So this may be a good path to the following study. Yeah.
But how is that PK map, the PK site relative to your superlative site?
How I can, if I can try if just mutate the phosphorylation site, PK phosphorylation site.
No, I'm saying relative position. Do you know where the map PK site is relative to the simulation site?
Oh, PK phosphorylation site is at the serine 169, and the simulation site, the current known sumo site is at 368. Yeah, there's quite a distance. So probably if there's a connection, it probably needs conformational change of this protein in order to get them both together. That's my guess.
The other substitute, I thought it's on PAT.
P45. Sorry, P45 can be simulated, and the simulation site, if I'm not mistaken, it's at lysine 368. And pKa is at serine 169. So 169 and 368, that's the distance. So my guess is the phosphorylation
I thought it's a PAT.
Our PAT is 14, lysine 14.
Okay, so you think it's not a stimulation of the PAT?
No. So we only focus on P45. Well, PAT is something that we just come up from.
Yeah, PAT is well studied, and also I think PAT are not made from homodimer.
Yeah, it's known.
So that's quite different from P45. P45 cannot form homodimer.
Yes. At least there's no study showed that P45 itself forms homodimer. Yeah.
But if you are going to study the effect of phosphorylation, it's a little bit more complicated. PAT can also affect P45. So how do you differentiate between these two?
I probably will first focus on this complex. I will still stay focused on using the in vitro system to study this using this complex. Mutate the phosphorylation site, as I said just now, and first test whether the simulation of particular P45 can be enhanced by pKa. If pKa if the phosphorylation mutated P45, if the simulation of P45 is lost in the mutant, which means there's a real connection between the phosphorylation and simulation of of P45.
Lost in what mutant?
In the phosphorylation site mutant.
Where? PAT or the
P45. I only focus on P45.
I know you want to focus on, but PAT is there, right? Whether you want to focus or not, it's there. So how are you going to differentiate between these two?
Differentiate. I think it's quite difficult because P45 alone, from the result, P45 alone, even though you added how much amount of the pKa, it still cannot be simulated. So, as I said, I still have to use a complex with containing PAT, yeah, to do the further study. That's, I think, the first thing I can make it clear, yeah. And is there any questions? Okay, I'm just going to give Shirley my acknowledgement. I would like to thank Wang Zhaoyan老师for very supportive and helping me so much in the two projects. I also want to thank our previous lab members, Yang, Xiaotou, and Herbie. And also in the second project, I want to thank Zheng Kun 老师 and Xu Yiqiao 学姐 for also giving me a lot of information and were very helpful. And also I want to thank Liu Fangwei, also gave me a lot of suggestions and opinions, as well as my lab mates, Yu Wei, Qi Wei, Xiao Zheng, and all these people. So thank you very much.